Now let us discuss about analytical treatment of half-wave rectifier. Let instantaneous value of AC voltage applied across the terminals AB is EAV equals to E naught sin omega t, where omega is the angular frequency of the AC. Let when the diode is forward biased, the resistance of the diode is RF and is infinity when reverse biased. Let RL is the load resistance. The instantaneous value of current through load resistance RL is I equals to Im sin omega t for the time 0 to t upon 2 and I equals to 0 for the time t upon 2 to t. Here Im equals to E naught upon Rf plus RL. The potential drop across load resistance is V equals to Em sin omega t for the time 0 to t upon 2 and V equals to 0 for the time t upon 2 to t, where Em equals to RL into E naught upon Rf plus RL. The output of the rectifier is discontinuous and fluctuating DC. The fluctuating DC consists of sum of pure DC and AC of different harmonics. Hence, by using the Fourier series, the output current I can be written as I equals to IDC plus sum over n equals to 1 to infinity Is sin n omega t plus sum over n equals to 1 to infinity Ic cos n omega t. By using the Fourier transforms, we may solve for the values of IDC, Is and Ic. So on solving, we get I equals to Im upon pi, which is the DC part, plus Im upon 2 sin omega t minus sum over n equals to all even numbers up to infinity 2 Im upon n square minus 1 into pi cos n omega t. This part represents different AC harmonics. Now let us calculate average value of output current. The average value of current is IDC equals to 1 upon t integration 0 to t IDT. Now let us divide it into two parts. So IDC equals to 1 upon t integration from 0 to t upon 2 IDT plus integration from t upon 2 to t IDT equals to 1 upon t integration from 0 to t upon 2 Im sin omega t dt plus integration from t upon 2 to t 0 dt, because for second half cycle I will be 0. So IDC equals to Im upon pi. Now let us calculate RMS value of output current. The RMS value of the current is the root of the mean of the squares of the current. It is given by IR equals to under root 1 upon t integration from 0 to t I square dt equals to under root 1 upon t integration from 0 to t upon 2 I square dt plus integration from t upon 2 to t I square dt. Here also the second part will be 0. So IR equals to Im upon 2. Now let us calculate the RMS value of AC component of current in output current. We know that IR square equals to IDC square plus IAC square. So IAC square equals to IR square minus IDC square. On substituting the values of IR and IDC, we get IAC equals to Im under root 1 upon 4 minus 1 upon pi square equals to Im upon 2 pi under root pi square minus 4. Now let us calculate ripple factor of half wave rectifier. The AC component present in the fluctuating DC is measured in terms of ripple factor and is defined as the ratio of AC current IAC to DC current IDC in fluctuating DC. It is represented by the symbol gamma. The ripple factor of output current of half wave rectifier is gamma equals to IAC upon IDC. Now put the values and we will get gamma equals to under root IR square minus IDC square upon IDC. Now by solving this we will get gamma equals to 1.21. Since IAC is greater than IDC, the half wave rectifier is poor rectifier. Now let us calculate the efficiency of half wave rectifier. The efficiency of rectifier is defined as the ratio of DC output power to the AC power supplied to the rectifier. The output DC power PDC equals to IDC square into RL equals to Im upon pi whole square into RL, and input AC power PAC equals to IR square into RF plus RL equals to Im upon 2 whole square RF plus RL. For ideal PN junction diode R equals to 0, so efficiency eta equals to PDC upon PAC equals to 4 upon pi square RL upon RF plus RL. So eta equals to 4 upon pi square, which is nearly equals to 0.406. So eta equals to 40.6%. That is, the efficiency of half wave rectifier is 40.6%. Now let us discuss about peak inverse voltage. Peak inverse voltage is the maximum voltage across the diode during the non-conducting period of the diode. When the diode is reverse biased in negative half cycle, the diode does not conduct and behaves as the terminals of no load, and hence voltage across the diode is equal to applied voltage. The maximum value of applied voltage in the negative half cycle is the peak value of the voltage, and hence PIV in half wave rectifier, that is peak inverse voltage in half wave rectifier, is EM. The peak inverse voltage should be less than the breakdown voltage of the diode. Otherwise, the breakdown of the diode will take place and diode will start conducting in the negative half cycle, and hence rectifier will lose its application.